Hello guys, welcome back. Myself Assistant Professor Gaurang Prajapati from Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. In the previous video, we have covered the theoretical criteria of the topic plastic design and the examples regarding shape factor. Okay. Now in this video, we are going to solve some of the examples by analytical method. Okay. Now talking about analytical method. See, there are basically two methods of analysis. See, with the principle of the virtual work of the upper and lower bound theorem, a structure can be analyzed for its ultimate load by one of the following methods, or we can say any of the following methods. And two methods are there: static method as well as kinematic method. Okay. Say, talking about static method, just let me give you overview. Okay. Static method is based on the static or lower bound theorem. In this method, free bending moment diagram of the structure due to the applied load is drawn and bending moment diagram due to redundant is superimposed over it to obtain the net moment distribution. Okay. So in simple words, for example, a simply supported beam is there. Say cantilever beam is there, prop cantilever. Okay. Say central point load. Say, so what we need to do? First of all, we need to do the redundant from this one. Okay, and we need to draw the diagram for the simply supported beam with central point load as well as moment diagram with respect to this fixed support. Okay, after that we can easily get the value of load and moment. Similarly, kinematic method. See, kinematic method is based on the kinematics or upper bound theorem, while previous method was based on lower bound theorem. This is consisted of locating of plastic places of the plastic hinge. In this one, we need to identify the places where plastic hinges are formed, and based on that, we will create the mechanism. Okay, we will see that in the example. So let's solve the examples. First of all, say, starting the first method, that is plastic method. Just a minute. Okay. See, now static method. Find the collapse load or plastic moment of the prop cantilever beam with the central point load. See, so now prop cantilever beam is there. So prop cantilever beam, as you can see in the figure, this one is our prop cantilever beam with the central point load. So L by 2, L by 2. Now we need to solve it by the static method. So what we need to do, first of all, say, let's remove, see, as we can find out the SI will be capital R minus small r. Okay, over here 3 reactions will be there, plus 1 reaction, minus 3 means equilibrium condition, this one. So answer will be 1. We need to remove 1 reactions. Okay, so simple. What we are doing, first of all, say removing this fixed support. So ultimately vertical reaction moment as well as horizontal reaction is also there, but as there is no external horizontal load in the beam, so I am avoiding this condition. Okay, so ultimately we got 2 reactions, moment as well as vertical. Over here we can say vertical reaction is there. So what we will do, first of all, we will draw the diagram based on this one. Simply supported beam with central point load. We all know that formula will be WL by 4 and its diagram will be like this. Positive, we can say WL by 4. Then the remaining one will means talking about the redundant, that is moment. So drawing the moment diagram, it will be like this. Okay, over here for example MP, and over here right hand side it is 0. Then just combine these two diagram, so you will get the main diagram of this one. Okay, so let's see, just a minute. See how the diagram is drawn. First of all, this one is simply supported beam with central point load. Say this diagram, that's WL by 4. And talking about the redundant diagram of the moment, say over here moment is there, MP. Okay, so its diagram is like this. So ultimately we will get our final diagram. Okay, this is our final diagram. Okay, this is the combination of simply supported diagram, means bending moment diagram, as well as redundant diagram. Okay, now so solving this one. Now talking about moment, so first of all, basic rule, say once we draw this moment diagram in this one, okay, so above it moment is final, this is one, this one is the fixed, MP will be produced over here. Now we need to calculate this moment, say this one. So how this is calculated? So for that one, explanation is given over here. We can simple use the two different kind of, either we can calculate it with reference to the average, or with reference to the proportion. Say first of all applying the proportion rule. Say this one. How? Say at the distance of L it is MP. See, at the distance of L it is MP. So at the distance of, we can say this one is L by 2 at the center. So at the distance of L by 2 it is how much? So simplifying this one we will get answer MP by 2. So I can get the answer this one, MP by 2. So this is the rule of proportion. Or you can directly calculate it with reference to average. Say over here moment is MP, over here moment is 0. So we can say average MP equals to this one plus this one divided by 2. See, MP plus 0 by 2. So ultimately I will get MP by 2. You can select any of the method whichever suitable to you. Okay. So I got this MP by 2. So finally what happens, what does it mean? Say these two moments means the total moment WL by 4 is subdivided into two moments. This one is MP and this one is MP by 2. So we can say from statics MP plus MP by 2, this one equals to total moment, that is WL by 4. So simplifying this one we will get 3 by 2 MP on the left hand side equals to WL by 4. So if I am concerned about the W or WC stands for the collapse load. If I am concerned about the WC, then I can calculate the WC, that is 6 MP by L. Say 4 will be over here, 3 into 4 12, 12 by 2, that will be 6. So 6 MP by L if I am concerned about the collapse load. And if plastic moment has been asked, then we can make the formula of the MP, this one. Okay. So WL by 4 on the right hand side and 2 by 3 will be on the opposite side. Okay. So ultimately we can say MP will be WL by 6, like that. Okay. So finally these are the formulas which will be used in the analysis method. Okay. Just I am explaining its derivation. Okay. So this one is the formula of the W and this one is the formula of the load of the beam, prop cantilever beam with central point load. Similarly, let's solve the another example. See, second one. Find the collapse load or plastic moment for the prop cantilever beam subjected to UDL, that is W kilonewton per meter, over the entire span. Okay. So as we have done in the previous example, first of all draw the beam, that is prop cantilever beam, and subjected to UDL over the entire span. So first let's remove the redundant. So like previous one, moment will be released over here, vertical reaction RA, or we can say VA, whatever we can say. This one will be RB or VB, like that. So first let's draw the diagram for the simply supported beam with UDL over entire span. So formula will be WL square by 8. So mid span moment, that is WL square by 8. Now moving forward. Now next, this moment is applicable over here because of fixed support. Over here moment will not be there, free, that is simple or hinge or roller support at the end. Okay. So moment will be 0 and over here moment will be MP. So ultimately diagram will be like this. Okay. Meanwhile mid span moment diagram is this one. Okay. So as we discussed previously, first of all this MP will be definitely there, that is MP. Now we need to calculate this MP. So as we discussed in the previous one, we can calculate this moment with respect to proportion, or we can say with respect to average. Okay. So I will prefer the average method. So explanation, average MP equals to left hand side's moment plus right hand side's moments divided by 2. So left hand side is MP, right hand side is 0. As you can see over here, MP plus 0 by 2. So ultimately MP by 2. So I will get this moment MP by 2, that is this one. Okay. So from the static, what will happen, this WL square by 8 total moment will be divided into two parts, MP plus MP by 2. Say, so from the statics, MP plus MP by 2 equals to WL square by 8. So ultimately simplifying this one, 3 by 2 MP equals to WCL square by 8. Okay. WC stands for the collapse load. So if we need to calculate WC, so by simplifying this one we can say it is 12 MP by L square, and if we want to calculate the moment, then MP equals to, we can say WC into L square by 12. Okay. So this one is the formula for the load as well as moment for the prop cantilever beam with UDL over entire span. So firstly, in first two examples, what we have done, we have solved first case prop cantilever beam with central point load and in this one prop cantilever beam with UDL over entire span. Now let's change the beam. Say instead of prop cantilever beam, let's take the fixed support. Okay, so as you can see, example number 3. Find collapse load or plastic moment for the fixed beam of the length L subjected to concentrated load W at the center. Okay, so fixed beam is there, this one, and central point load is applied, that is W. Okay, now so we need to calculate its collapse load, or we can say plastic moments formula. So as we were doing in the previous examples, we need to do the same one. Now fixed suppose reactions will be, as we discussed, moment as well as vertical reaction. Similarly over here also same thing will be happen, vertical reaction and moment, two reactions will be there. So let's draw the first diagram for the simply supported beam with central point load. So moments formula will be simply supported beam with central point load WL by 4. So ultimately we will get this diagram, WL by 4. Now talking about moment, okay, over here, just a minute, over here moment is there MP like this, so its moment will be like this MP. Similarly on the right hand side again MP is there, so similarly we will get MP over here, this one. Let's connect these two. So this will be our final diagram, this is our final diagram. Okay, so let's talk about the explanation. First of all, mid-span moment, that is WL by 4, simply supported beam with central point load. Now talking about the another moment. So now first of all let's discuss the diagram once again. See, this one was mid-span diagram, while this one was moment diagram, redundant moment diagram. Okay, this MP. Now as we discussed earlier, this MP will be produced, that is fixed. Okay, now we need to calculate this MP, this one. Okay, so by using the average method, left hand side moment plus right hand side moment divided by 2. So average MP equals to left hand side MP plus right hand side MP divided by 2. So ultimately 2 MP by 2, so I will get the value MP. So this MP will be obtained like this. Okay, now from statics, this MP plus this MP equals to total moment. So MP plus MP equals to WL square by 2. Okay, just a minute. So now, so we got this one. So what will happen? Let's explain once again, I was interrupted. So MP plus MP, that is equals to WL by 4. So from the static, MP plus MP equals to WL by 4. So we can say twice MP equals to WL by 4. So if we want to calculate WC, then WC equals to, we can say 8 MP by L, or we can say if plastic moment is asked, then we can make the formula for the MP. The formula of MP will be WC into L divided by 8. Okay, so this one is the formula for the fixed beam with central point load. Okay, similarly let's take the UDL load over here. Example number 4. See, find the collapse load or plastic moment for the fixed beam subjected to UDL over the entire span. Okay, now so first draw the diagram, fixed beam with UDL over the entire span of the length L. Now let's take the redundant, say MP, and vertical reaction V or RA. Similarly vertical reaction VB or RB and MP will be there. Okay, so first draw the span diagram of simply supported beam with UDL, that will be WL square by 8, its span moment, that is WL square by 8. Then talking about MP's diagram, then over here it will be MP, over here it will also be MP because of fixed support. So ultimately diagram will be drawn like this. Okay, so ultimately we got this diagram. See, this one is the diagram for the moment, that is MP, and this one is the span moment bending moment diagram, that is WL square by 12, WL square by 8, sorry. Now as we discussed earlier also, this MP will be definitely produced. We need to calculate the below 1 MP, that is this one, we need to calculate this one. So by using the average method, MP plus MP divided by 2, say average MP equals to MP plus MP by 2, so we'll get MP. So this MP is like this. Okay, so now by using the static, this MP plus this MP equals to WL square by 8. So MP plus MP equals to WL square by 8. So twice MP equals to WL square by 8. So ultimately, if you want to calculate WC, then it will be 16 MP by L square, and if you want to calculate MP, then it is WC L square by 16. Okay, so we solve the 4 different beams. Okay, first we saw, just a minute, let me do the figure over here. First, prop cantilever beam with central point load, and another one prop cantilever beam with UDL. We derive the formula for that one. And in the last 2 method, we took fixed beam with the central point load and then fixed beam with UDL over entire span, like that. So we have derived all the formulas for the moment as well as we can say collapse load for all these 4 beams. Okay, and these formulas will be used in the design of the beam. Okay, then okay, let me show you some of the formulas which we have derived. See, this one is the formula which we derived. Just see, first one, prop cantilever beam with central point load. As you can see in the figure, the moments formula is WL by 6, by load's formula, that is W's formula, will be 6 MP by L. We have derived just before this one. Then prop cantilever beam subjected to UDL over the entire span. So moments formula WL square by 12, loads formula 12 MP by L square. Third one, fixed beam with the central point load, formula WL by 8, this one is 8 MP by L. Last one, fixed beam subjected to UDL over the entire span, moments formula is WL square by 16, while loads formula is 16 MP by L. Okay, so we have derived all these 4 formulas using the static method. Now let's solve the another example. Just a minute. See, this kind of example has been asked in the exam. Okay, so let's solve this one. Example number 5. See, determine the collapse load for the fixed beam of the span L subjected to load W kilonewton per meter on the left half of the span. So first of all, fixed beam is given to us. So first of all, draw the fixed beam. Now they have mentioned that the load is acting on the left half span. Okay, so that is at the span of L by 2. Apply the UDL load, that is W kilonewton per meter. Okay, now we have already derived the formula for the moment and load for the previous one, fixed beam subjected to UDL over entire span, but in this case we can notice that UDL is acting only up to the half span, not over the entire span, so we cannot apply directly moments formula in this one. Okay, so let's solve this kind of sum. So first of all, let's release the structure, we can say support. Say by releasing the fixed beam, fixed support, we will get moment as well as reaction. Same thing over here also, vertical reaction and moment by releasing the fixed support. Now let's find first of all its reactions. So in reactions, let's take moment at A, sigma m equals to 0. So anti-clockwise moment, say RB into, we can say whole distance is L, that will be anti-clockwise, RB into L. Now talking about clockwise moment, then this load's moment will be obviously clockwise, UDL, so load into distance into half distance, so W into UDL is acting upon the span L by 2, so W into L by 2 into L by 4. By simplifying this one, we will get RB, that is WL by 8. Now let's calculate RA. Say sigma V is equals to 0, upward equals to downward. Talking about upward load, that is RARB, and talking about downward load, that will be W of the span L by 2. So total load will be WL by 2. Okay, so RA equals to WL by 2 minus WL by 8. So total load minus RB. By simplifying this one, we will get RA, that is 3 by 8 into WL. So we got our 2 reactions, RA as well as RB. Okay, so now let's find the point where maximum bending moment occurs. See, maximum bending moment will always occur whenever SF is 0. So let's find its location. See, let's take section XX at the distance of X from the A. Okay, let SF at X equals to 0. Let me draw the beam over here. Say for example, this one is our beam. Okay, this one is our UDL of the half span, that is L by 2. Now W kilonewton per meter. Now let's assume that SF at the distance of X, for example over here, let's take a section XX at the distance of X from A. So let's assume that SF at this point is equals to 0. So sigma V equals to 0 in this portion. Okay, so simple, upward is plus, downward is minus. Talking about upward, then RA will be there, that is will be upward. So RA minus this portion's UDL, W kilonewton per meter of the distance x. So that is acting downward direction though, so it is taken as negative. So RA minus W into x. Okay, this one. So let's put the value of RA. 3 by WL minus WX equals to 0. By simplifying this one, WW will be cancelled. So x equals to 3 by 8 into L. So we got the value of distance where SF is 0, that is 3 by 8 L. So obviously bending moment will be maximum at this point. Okay, so let's take the moment at that point. Let me draw the diagram once again. Just a minute. See. So now we got, just a minute, let me draw the diagram first of all. This one was L by 2. Now we got the distance. Say for example this one is our x. Okay, we got this the value of x, that is 3 by 8 into L. We need to calculate moment over here. Now this one is, we can say RA, while this one is W kilonewton per meter. Okay, so simple. Let's take the moment over here. So RA into x clockwise, so plus, and W's moment will be obviously anti-clockwise, so W into x by 2 as per the UDL rule. Now we get the value of x, that is this one, 3 by 8. Let's put down the value. RA 3 by 8 into WL, x that is 3 by 8 into L, minus UDL W, x 3 by 8 into L, and x by 2, that means 3 by 16 into L. By simplifying this one, we will get 9 by 64 into WL square, and by solving this one we will get 9 by 128 WL square. Okay, by simplifying these two terms we will get mx equals to 9 by 128 WL square. So this is the maximum bending moment which can be produced over the half UDL acting fixed support. Okay, so now let's do the same things which we were doing earlier in the all four previous examples. Now see, this one is the reactions, this one is the reaction. Now over here MP is there, over here MP is there. Now we got the moment, that is 9 by 128 WL square. This one is the maximum bending moment at the SF is 0. Okay, so dimension is there, that is x. Then talking about moments diagram, this one is MP, so over here MP, again on the right hand side this one is MP, this one is MP. Then connect this to one. Okay, now as per the rule, this moment will obviously will be MP. Okay, now we need to calculate the below moment, that is this one. Okay, same thing will be there, left hand side MP plus right hand side MP divided by 2. Let's take average of this one obviously, so this will also be MP. Okay, so see, average MP equals to MP plus MP by 2, so we will get this one as a MP. Now by the static, this MP plus this MP equals to total moment. So from the static, MP plus MP equals to 9 by 128 WL square. So twice MP equals to 9 by 128 WL square. So ultimately, if collapse load has been asked, then WC equals to 256 by 9 MP by L square. And if moment has been asked, then we can calculate moment as well as, that is 9 by 256 into WC into L square. Okay, so this was the case where fixed beam was supported by, was acted by half UDL span, that is W kilonewton per meter. Okay, so this is the method of static method. Okay, so guys, now let's some examples using the kinematic method. Okay, so now in this one let's solve the data. Determine the plastic moment capacity for the given continuous beam. Now in this one a continuous beam is there. Say continuous beam is the beam which contains more than 2 supports. Okay, now as you can see 1, 2 and 3 supports are there. So this one is a continuous beam. Now in this one, on the span AB central point load is there, while on the span BC UDL is there, that is of W kilonewton per meter. So let's solve this example by taking each span separately. So first let's take the span AB. Okay, now as you can see at A simple support is there, and at B, now B will be the intermediate support in the continuous beam ABC. So B will act as a fixed beam. Okay, that is fixed support. So ultimately if I draw the figure of span AB, it will be like this. It will act as a prop cantilever beam. At B it will act as a fixed support, at A it will be the simple support. Okay, so in the span AB, as we can see, let me do the figure once again. This one is a fixed support at B, and at A it will be a simply supported. Okay, so at A moment will not be produced, and at B due to fixed support moment will be produced, that is MP. Okay, over here it is 0, while central point load will be as it is, that is central point load. Okay, now let's draw the diagram. Simply supported beam with central point loads, we know that formula will be, that is WL by 4. But in this one, what we are doing, in this one we will solve this method using the kinematic method. So in the kinematic method we need to create a mechanism. So how to create a mechanism, let me zoom the figure. First of all, see, now first of all, see, this one is our simply supported beam, so deflection will be there because of the point load, so deflection will be like this. Okay, so let's do the mechanism. So how to draw mechanism? First of all, place beam as it is, like this. Okay, L by 2, L by 2. Now at the center deflection will be there, so let's make a triangle at the bottom from the center, like this. Now over here rotation will be there, that is theta 1, over here theta 2, and over here both theta, summation of both theta, we can say theta 1 or theta 2, or you can draw figure like this also, say central point load W. Okay, so you can draw figure like this. Okay, theta 1, theta 2, and over here also theta 2 and theta 1. You can show theta on both sides also over here, or you can show like this on one side, that is completely up to you. Okay, so now just a minute. So now talking about moment will be produced over here like this. So over here moment is produced, and at the center also moment will be produced. Over here also moment will be produced at the location of the point load. So ultimately we got two moments, one at the right hand side and one at the center. Okay, so first of all let's derive the relation between these two theta 1 as well as theta 2. So just a minute, see explanation. Say right hand side dimension, sorry, left hand side dimension L1 by 2 into this theta 1. So L1 by 2 into theta 1 equals to right hand side dimension, that is L1 by 2 into theta 2. So L1 by 2 into theta 2. So ultimately we will get theta 1 equals to theta 2. Okay, so we got the relation. Say as central point load is there, or we can say over the whole span UDL will be there, theta will be equal, okay, on the both sides. It will be unsymmetrical, or we can say in case of the eccentric load unsymmetrical theta will be there. Now let's find the theta first of all. So let's take any of the triangle out of these two triangles, say this one. Now this one is L1 by 2, this one is our deflection, that is delta x, and this one is our angle theta 1. So from this figure I can say tan theta 1 equals to delta x divided by L1 by 2. Okay, this one delta x divided by L1 by 2. So delta x equals to cross multiplication L1 by 2 into tan theta 1. Say assume the tan theta is very small, so ultimately I will get delta x equals to L1 by 2 into theta 1. So that is the formula of delta x. So we got the value of the deflection, that is this one, delta x. Now in the kinematic method we need to calculate work done too, that is external as well as internal. So first of all external work done. So external work done's formula will be always common, that is load multiplied by its deflection, that is delta x. So W into delta x. Delta x we have already derived the value of delta x, that is L1 by 2 theta 1. So W into L1 by 2 into theta 1. So this is the case of external work done. Talking about internal work done. So in case of the internal work done, we need to consider the point, or we can say locations where moment is applicable. So as we can see, moment is applicable on the right hand side. So first MP will be this one, MP into theta 2. Over here theta 2 is this one, theta 2. Okay, that is first one. And next, that is over here also moment will be produced. Okay, so MP in the bracket theta 1 plus theta 2. Okay, we cannot take the point A over here, because over here no moment is there. Say we can see over here at A simple support is there, so we cannot take moment over here, so ultimately that point is neglected. So we got the MP into theta 2, that is this one, and MP into theta 1 plus theta 2, that is this one. So by simplifying term, MP into theta 1, this one is MP into theta 1 plus theta 2. Now as theta 1 equals to theta 2, so this will becomes theta 1. Okay, so ultimately it will be 3 MP theta 1. Okay, now by the principle of virtual work, we need to equal external work as well as internal work. External work is W into L1 by 2 theta 1, while internal is 3 MP theta 1. By simplifying this one, we will get the formula of the MP, that is WL by 6. Okay, so this one is the final formula. Now if you remember, we have already derived this formula. Say this one is the case of prop cantilever beam central point load. Remember the formula WL by 6. Okay, let me show you the formula. Say this one, just a minute. See, prop cantilever beam with central point load, the moments formula is WL by 6. So we have already solved this one, or we can say derive this formula using the static method. By kinematic method also we can derive the same formula. Okay, so now coming back to the sum, now let's take the another span, that is BC. Now as because of intermediate support, B will act as a fixed support, while C at the end will be act as a simple support. So ultimately it will also be the case of prop cantilever beam with UDL over the entire span. Now because of fixed support over here, MP will be produced. Okay, now let's draw the diagram. See this one. See, our main diagram is B intermediate support, C corner support. So at B moment will be produced, this point, and this one is our C. Okay, over the whole span UDL is there, so ultimately we will get this diagram. Okay, that is W kilonewton. Now talking about span, that is L2. Now once again we need to create a mechanism over here. So first of all, take the beam as it is, this one, that is W kilonewton per meter. Okay, now deflection will be there. Say let's divide the distance into two parts, L2 by 2, L2 by 2, that is this one. Okay, now this one is our deflection. So first of all, do the same thing, make mechanism like this, like this. This one is theta 1, this one is theta 2, while this one will be theta 1 plus theta 2, that is this one. Okay, now let's derive the relation between, we can say, theta 1 as well as theta 2. Now L2 by 2 into theta 1, L2 by 2 into theta 1 equals to L2 by 2 into theta 2. Okay, so L2 by 2 will be cancelled, so ultimately theta 1 equals to theta 2. As I told you earlier also, in case of the simply supported beam with central point load or simply supported beam with UDL, our theta will be common, or we can say equal. Now from the figure, say let's calculate the theta 1 from this one theta 1, this one is L2 by 2, while this one is deflection. So from the figure I can say tan theta 1 equals to delta x into L2 by 2. So delta x equals to L2 by 2 into tan theta 1. So tan theta is very small, so ultimately delta x equals to L2 by 2 into theta 1. Okay, now let's find first of all external work done. So in case of the UDL, the formula will be changed. The formula will be of external work done will be total UDL, that is W into L, into this deflection by 2, that is delta x by 2. We have already derived the value of delta x, that is L2 by 2 into theta 1. Okay, so putting down the value, W into L2, that is total UDL. Okay, so W into L2 into delta x by 2. Now let's put down the value of delta x by 2, that is L2 by 2 into theta 1. By simplifying this one, we will get WL2 square by 4 into theta 1, that is average deflection due to the UDL, that is external work done. Now talking about internal work done, so we need to consider the point where only moment is producing, means on the left hand side as well as at the center. Now on the right hand side no moment will be there, as it is a simple support at the end. Okay, so first one MP into theta 1, that is of left hand side, and central one, that is MP into theta 1 plus theta 2. Now as theta 1 is equals to theta 2, so ultimately all are the theta 1, so ultimately we will get 3 mp theta 1. Okay, now equal the both work done, external as well as internal. External WL2 square by 4 into theta 1, that is this one, and internal, that is 3 mp theta 1, that is this one. By simplifying this one, we will get mp equals to WL2 square by 12, or in simple word WL square by 12. Okay, so now if you remember, we have derived this formula earlier also. Let me show you. WL square by 12, we have got the formula. Remember the formula, just a minute. Case number 2, see, prop cantilever beam UDL over entire span, moment's formula was WCL square by 12. Okay, so from using the static method, we have done the same thing. Okay, so this one is the case of the continuous beam, solving the case of using the kinematic method. Now let's solve the another sum. Now this time let's take the fixed beam. See, in the previous one, what I have done, I have taken the simply supported at the corner, simple support at A and C. Now instead of the simple support, let me take this time fixed support, that is this one. Now as you can see in the figure, just a minute, example number 7, determine the plastic moment capacity of the given continuous beam. Okay, now at A, B, C, 3 supports are there, so it will be the continuous beam. Now this time at A and at C, fixed supports are there, and B, because of intermediate support, it will also act as a fixed support. So ultimately all the individual spans, say AB as well as BC, both will act as a fixed support. Okay, so let's solve the sum like earlier as we done in the previous example. Say let's take span AB. Now A is fixed support, B because of intermediate it will also act as a fixed support. Now central point load is there, W. This one is L1 by 2, this one is L1 by 2. Okay, like that. So for this one, at left hand support MP will be there, at right hand support also MP will be there because of the fixed support. Okay, so let's create a beam mechanism. Draw the beam as it is, W. We need to always draw the mechanism like this in the triangle shape. See, theta 1, theta 2. Okay, let me zoom the figure so you will get easily. See, like this one is theta 1, this one is theta 2, while this one theta 1 plus theta 2. And because of left hand side fixed support, MP will be there. Because of right hand side fixed support, MP will also be there. And at the center also moment will be there, like this. Okay, so let's derive the formula, or we can say relation between theta 1 and theta 2. So we can say theta 1 into L1 by 2 equals to theta 2 into L2 by 2. So we will get ultimately theta 1 equals to theta 2 because of central point load. See, just a minute. See, that's it, the explanation. L1 by 2 into theta 1 equals to L1 by 2 into theta 2. This one, L1 by 2 will be cancelled, so ultimately theta 1 plus theta 2. Now from the figure, let's take one of the triangle. Let me zoom the figure. See, for example this one, I am concerned about theta 1. This one is delta x, this one is L1 by 2. So tan theta 1 equals to, we can say delta x divided by L1 by 2. So ultimately delta x equals to L1 by 2 into, sorry, L1 by, just a minute, 2 into theta 1. Say let's assume tan is very small. Okay, see, using this triangle, tan theta 1 equals to delta x into L1 by 2. So delta x equals to L1 by 2 tan theta 1. So ultimately L1 by 2 into theta 1. So let's assume tan theta is very small. Talking about external work done, load into deflection. Load is W, deflection is delta x, that is this one. Put down the value over here. So we will get W into L1 by 2 into theta 1. Now let's talk about internal work done. Now talking about internal, first of all this MP will be considered, so MP into theta 1. Then central's MP will be considered, so MP into theta 1 plus theta 2, and then right hand side MP will be considered, so MP into theta 2. Now as we know that theta 1 equals to theta 2, so this theta 2 and this theta 2 will be converted into theta 1. Okay, so ultimately all are theta 1, so summation will be 4 MP theta 1. Now let's equal the both work. External work equals to internal work. External work W into L1 by 2 theta 1, while interval is 4 MP theta 1. So ultimately simplifying this one, we will get formula MP equals to WL1 by 8, or we can say WL by 8. Okay, let's keep it as a constant, WL by 8. So this one is the case of fixed beam with central point load. Let's see the formula which we did earlier using the static method. Just a minute. See, fixed beam with central point load, moment's formula was WL by 8. Okay, now let's take the another span, that is BC, the same sum. Now say let's talk about BC. So in case of BC, C is already fixed support, and because of intermediate support, B will be also converted into fixed support. Now so beam will be like this, left hand side moment will be produced, right hand side also moment will be produced. Okay, so span BC. See, first of all draw the beam, that is either show as a UDL W kilometer meter, or you can convert it into the point load also, load into deflection, and apply it at the center like this. You can show like this, WC into L, that is up to you. You can use the both parameters. Okay, so we were just a minute. So now draw the mechanism, that is like this, theta 1 theta 2, and over here theta 1 plus theta 2. Because of fixed support, left hand side MP, over here also because of fixed support, right hand side MP, and at the common center moment will be there, and this one will be our deflection delta X. Okay, so as we were doing, first of all derive the formula between the theta 1 and theta 2. So on the left hand side L2 by 2 into theta 1, and on the right hand side L2 by 2 into theta 2. L2 by 2 will be cancelled, so theta 1 equals to theta 2. So first problem is solved. Now let's derive the value of delta X. So this triangle, this one is L2 by 2, this one is delta X, this one is theta 1. So we can say tan theta 1 equals to delta X divided by L2 by 2. So delta X equals to L2 by 2 into tan theta 1. So theta is very small, so delta X equals to L2 by 2 into theta 1. Okay, see, tan theta 1 equals to delta X divided by L2 by 2. So delta X equals to L2 by 2 into tan theta 1. So ultimately L2 by 2 into theta 1. Okay, now talking about external work done. External work done means, in case of the UDL we discussed earlier also, total load, that is W into L, we can say, that is UDL. Okay, into delta X by 2. Now W into L, L is we can say L2 che. So W into L2, and delta X by 2, delta X is L2 by 2 into theta 1 divided by 2. So ultimately we will get, by simplifying this one, W L2 square by 4 into theta 1. Okay, now let's talk about the internal work. So because of the left hand side MP, MP theta 1, because of the central MP, MP theta 1 plus theta 2, and because of the right hand side moment, that is MP into theta 2. And as we have already derived theta 1 equals to theta 2, so these two theta 2 will be converted into theta 1. So ultimately summation will be 4 MP theta 1. Okay, so by let's equal the external as well as internal. By solving this one we will get MP, so formula of the MP will be WL square by 16. Okay, let's keep it as a constant, WL square by 16. So this one is the case of fixed beam with UDL over entire span. So let's see the formula which we derived earlier. See over here, fixed beam with UDL over entire span, we got the moments formula WL square by 16. Okay, so by using both static as well as kinematic method, we have derived the all four spans formula. Okay, that is this one. And as I discussed earlier also, over here I have given the overview of the cases. Say first one, prop cantilever beam with central point load, so formula of the moment will be WL by C. Usually we need to remember the formula of moment only. Normally collapse load will not be asked. Usually we will use these formulas in the design. So formula of the moment is WL by 6 in case of the prop cantilever beam with central point load. Second, prop cantilever beam with UDL over the entire span, formula will be WL square by 10, that is 12. Then third case, fixed beam with the central point load, formula is WL by 8, and fixed beam with UDL over entire span, formula is WL square by 16. Okay, these are the main four formulas which will be used during the design. Now while designing the beam, we will to solve this kind of sums also. Like I have given the demo of the two span continuous beam, we have solved this one. So we know that in this kind of sum, B will act as B is a intermediate support, so B will act as a fixed support. So ultimately span AB will act as a prop cantilever beam, while at the same time span BC will also act as a prop cantilever beam, just because of B is intermediate fixed support. See, span AB and span BC, so both are end span, will act as a prop cantilever beam, and prop cantilever beam's original formula was WL square by 12. To be precise, 12 is round figure value, instead of 12 in the analysis it is taken as WL square by 11.656. okay, while now let's take the 3 span moment. Okay, 3 span beam. Now as B and C are the intermediate support, okay, so that will be converted into fixed support. So AB will be like this one is AB, while say giving the notation BCDA, and this one will be CD. So both AB and CD will act as a prop cantilever beam and span. Okay, so you can see span AB and CD and span will act as a prop cantilever beam, and its formula will be WL square by 11.656. While talking about the central span, that is span BC, obviously both B and C are intermediate support, so both will act as a fixed support, so ultimately span BC will act as a fixed beam. So span BC, that is intermediate or we can say central span, will act as a fixed beam, and we have already seen the formula of the fixed beam, that is WL square by 16. Okay, so these are the formulas which will be used during the design of the beam. Okay, thank you.